We've learned previously how to use Hess's law to find the total enthalpy change of a reaction by adding up the individual steps. This can take that one step further and talk about standard states. So we can use the standard enthalpies of formation that are listed in a table to calculate the standard enthalpy change for a reaction. We have the standard empathy. Oh my gosh. We have the standard enthalpy of formation for just about every compound that you will use in a common occurrence. They're not all in that table 6.2. You're going to need to use Appendix 4 at some point. This is in the back of your book, right in front of the glossary, the very last of the purple pages. But we know that the standard enthalpy change, and to tell us that we mean standard, we're going to put the little symbol there, and I'm going to put Rx in here for reaction, just so I know when I've got all this stuff listed what it means, is equal to the sum of the change in enthalpy of formation standard for the products minus the sum of that for the reactants. So all you have to do is look it up. If we look at our first product, NO2, we can look up that the standard enthalpy of formation for nitrogen dioxide is 34. But we don't have one nitrogen dioxide, we have 4. So we have to say, I'm going to put brackets because I'm going to need 34 times 4. And it was positive in our book, positive 34. And water, we're summing, has a standard enthalpy change of negative 286. And we have 6 water molecules, so we multiply by 6, minus the sum of the reactants. Our first reactant is ammonia, and its standard enthalpy of formation is negative 46. Now you might think, we aren't actually making it, we're not forming it, we're breaking it apart in this, so you should switch the sign. But that is already taken care of right here. This is accounted for already, so you just use the number out of the table. Negative 46 times 4. And then we have oxygen. Now you can look this up in the appendix if you need to, but this is a standard state. Diatomic molecule as a gas, so its enthalpy of formation is 0. That is broken down as far as you can get. That's what standard state means. When we add this up, we have to be really careful to do our math steps in the right order and multiply and then add. When we multiply over here, we get 136, and then we get negative 1716 and 184. We add these two together, we get negative 1580 minus negative 184, which ends up adding because it's a double negative. So our final standard enthalpy of formation is negative 1396 kilojoules. Let's try one more. This reaction runs booster rockets for space shuttles. This is a lot more complex, but but it's a good example because if you can do an example like this, you can do any of them. And you are going to have to use that Appendix 4 for these because they're not all in that table. So the standard change in enthalpy for the reaction is equal to the sum of the products, the sum of the standard enthalpies of formation for the products minus the reactants. If we look this up in the table, there's only one of these aluminum oxides. So we get negative 1676 plus, we have to look up aluminum chloride, negative 704 plus, we have 3 of these, so it's 90 times 3 plus negative 242 times 6. And then we have to subtract the reactants. Aluminum, that is a metal, as a solid, that is standard state, so it's 0. For this ammonium perchlorate, you can look it up, and we see negative 295 times 3. When we do the math here, we add up all these numbers, we sum them. We get negative 3,562 minus negative 885. We know 2 negatives become a positive. So our standard change in enthalpy for this reaction is negative 2,677 kilojoules. And hopefully when you read the question, you knew that this was going to be a negative and it was going to be large. This is a reaction that runs rockets that sends up space shuttles. So it has to put out a lot of energy. It has to be very exothermic. As long as you take these step by step, none of the math is hard. You just have to be able to look up the right numbers and stay organized. That's why I try to have very organized work, because it helps you not make math errors.